Doubt, I'll send message to you on WhatsApp group only. So in last class we discussed about stereochemical aspects of these haloalkane haloarene compounds, and that is their optical activity, right? Of how you decide whether the compound is optically active or not. Even we discuss method to find out that. Then different type of optical isomers like enantiomers, diastereomers. So about all that we discussed in detail yesterday. Now today we'll start with chemical reactions of haloalkane haloarene compounds. So what you mean by haloalkane haloarene chemical reactions? So in case of hydrocarbon, we already discussed about their chemical reactions. Under that we study different types of reactions of alkane, alkene, alkyne when they react with other such compounds, right? So here also we'll do the same. Haloalkane, haloarene when react to different compounds, which type of product will get, byproduct will get, about all that we'll discuss here in today's class. So our today's class is chemical reactions of haloalkane haloarene. Now in this we have to study three different types of reactions. Actually these haloalkane compounds, they give three different types of reaction. One is nucleophilic substitution reaction. Another one is elimination reaction. Third one is reaction with metals. So three different types of reactions we have to study under this: nucleophilic substitution reaction, elimination reaction, and reaction with metals. Nucleophilic substitution, in under that we have another subtypes, but that we'll see afterwards. So first let me start with nucleophilic substitution reactions. Now here heading itself suggests that this is a kind of substitution reaction. Substitution reaction means we have something present, and at that place we are removing something and adding something new element, right? Suppose we are replacing hydrogen with halogen, that is also kind of substitution reaction. So substitution means we have to replace one element or group by some another element or group. So that is what is substitution reaction. Now nucleophilic means nucleophile. What is nucleophile? So nucleophile is one which is having attraction towards nucleus, which is having attraction towards nucleus. So nucleophile means nucleus loving, one which has attraction towards nucleus. Substitution means they are removing something and at the place of that they are attaching themselves. So nucleophilic substitution reactions we have to study here in this class. Of course here we have to study about haloalkane, general formula if I write, that is Rx. Now as halogen is more electronegative, here we have partial negative charge, while here partial positive charge is present. As this is nucleophilic substitution, we have to react haloalkane with nucleophile. Nucleophile itself is negatively charged and has attraction towards positively charged ion. Now here this Rx bond is already polar bond. So whenever here I have bond cleavage, During bond cleavage, these bond electrons goes to halogen. Whenever there is bond cleavage, these bond electrons goes to halogen. So this is X negative, R positive. In the reaction mixture, I have nucleophile which has attraction towards nucleus. So as soon as there is formation of R positive in the reaction mixture, nucleophile immediately attack on R plus. And as I keep on telling you people that always there is transfer of electron, never transfer of nucleus is possible, and as per that rule, always nucleophile attack to the positively charged alkyl group, and so arrow comes from nucleophile to positively charged alkyl chain. Here if you see carefully, during this reaction, halogen detach from the alkyl chain and nucleophile attach to the alkyl chain. And so finally the product form is RNU. See here this lone pair of electrons which is there with nucleophile. Nucleophile sharing those electrons with this R positive alkyl chain, and as a result of this we'll have one bond formation between alkyl group and nucleophile by sharing of this lone pair of electrons. Along with this halogen liberate with one lone pair of electron as bond electrons completely transfer on halogen ion. Now here during this reaction, as halogen is leaving this alkyl chain, X minus is known as leaving group. Halogen is known as Lg. Lg is leaving group. So this is how this reaction occurs. This is the general reaction where this is substrate, this is attacking reagent, this is my product. Now in haloalkane, haloalkane compounds, this reaction proceeds via two different mechanisms. In haloalkane, nucleophilic substitution reaction that proceeds via two different ways, two different mechanisms. One is bimolecular nucleophilic substitution reaction, and another one is unimolecular nucleophilic substitution reaction. Now see here in this, when we study these two in detail, we need your knowledge regarding this optical activity, then this enantiomers, dextrorotatory, levorotatory, all these knowledge we need. So hope you have revised those topics and you are ready with that content also. Okay, so till now we discussed nucleophilic substitution reaction, nucleophile, one which is nucleus loving. So when haloalkane, they are exposed to nucleophile, halogens they get replaced by, or they get substituted by nucleophile, and the product form is RNU with the leaving group, that is Lg X minus. This proceeds via two different mechanisms, bimolecular nucleophilic substitution and unimolecular nucleophilic substitution. Before we go for this in detail, let me first have a clarification regarding the term nucleophile. So nucleophile, these are nucleus loving species, and their nature is to donate electrons to the one which is electron deficient. For example, we have monovalent nucleophiles, Monovalent nucleophiles are the one which has one lone pair of electron and donate one lone pair of electron to the electron deficient alkyl chain. Like we have OH minus. Here oxygen is carrying one lone pair of electron with one negative charge. Then OR minus. Then I minus. Then H minus. Actually H plus carry no any electron. Hydrogen carry one electron, but when we have H minus has two electrons present. Then we even have ambidentate nucleophile. Ambidentate nucleophile. Now what do we mean by ambidentate nucleophile? Now these are the nucleophiles which have two elements present with lone pairs. Like suppose for example if I say Cn minus. Now Cn minus, if we see structures, carbon is triply bonded to nitrogen. Now nitrogen is carrying one lone pair of electron. Carbon has 4 electrons in its outer shell. 1, 2, 3. In 3 bond formation, that is sharing 1 electron. So 3 electrons of carbon over here in formation of triple bond. One more electron of carbon is present. Carbon is gaining 1 electron from some outer source. And so that is having 1 extra electron. Whenever that is having 1 extra electron, negative charge is present on carbon. Now here, both these elements, they can donate electrons. Carbon can also donate or nitrogen can also donate. Any one of these two they will donate. Only any one of these two they will donate. But from any end this can attach, and this is the reason they are known as ambidentate nucleophile, which is having more than one species present which can donate lone pair of electron. Same way NO2 1 minus. One more example let me take. NO2 1 minus. Here again nitrogen. Nitrogen maximum capacity of forming bonds is 3. Here that is satisfying with one lone pair. Oxygen maximum bond formation capacity 2 with 2 lone pairs. But here if you see oxygen is forming only one bond, means 3 lone pairs with one more extra electron. See 1, 2, 3, 4, 5, 6. Here you see 1, 2, 3, 4, 5, 6. One extra electron is there. So negative charge. Again here even this nitrogen can donate and this oxygen can donate. So this is the kind of nucleophile which is known as ambidentate nucleophile. Ambidentate nucleophile. So this is what is about nucleophile. Now let me discuss about this reaction. First we have a number of nucleophiles which is having more efficiency to attach with alkyl chain than that of halogen, and because of that halogens get substituted by nucleophile, because tendency of nucleophile to attach with alkyl chain is more in comparison to halogen. Now this way we have number of nucleophiles. So let me just go through those nucleophiles and what is the product form. One by one let me go through this. Then when we discuss about this bimolecular and unimolecular, at that time we'll see again. So our general reaction is what? Rx plus Nu minus with one lone pair gives you Rnu plus X minus. See, by mistake also don't show lone pair over here. That lone pair, this nucleophile, this lone pair, this nucleophile is utilizing in bond formation. Now this nucleophile is not carrying any lone pair of electron. So if I have to show arrows, then this bond electrons transfer on halogen, and at the same time this nucleophile is attacking on the alkyl chain. Let me see some different examples of nucleophile. If Rx react with NaOH, this NaOH split into two part, Na plus OH minus. OH minus is act as nucleophile over here. So again these electrons get transferred on halogen and there's a attack over here. Product form is ROH plus X minus, and the product form is alcohol. Product form is alcohol. Same way, if I have water, Rx plus HOH, that is water, this also split into two part. Here again there is electron transfer, OX minus directly attack on alkyl chain, so the product form is ROH plus X minus alcohol. Instead, if I have NaHCO3, sodium, instead suppose if I have NaOCO3, CH3, that is sodium methoxide. Now in this case, again this cleave into two part, Na plus OCH3 minus, this transfer on alkyl chain, and the product form is ROCH3. Write name of this compound, means the functional group present in this compound, in comment box fast. Write name of the functional group present in this compound in comment box. What is this? Write. No any answer? Yes, correct Hitanshi. This is ether. ROR dash. This is ether. So when you react your alkyl halide with sodium ethoxide, the product form is ether. Next, if I have Rx plus NH3, that is ammonia. If bond cleave from here, this is H plus, this is minus, this get transferred over here, so this negatively charged part attack on the alkyl chain, and the product form is RNH2 plus X minus. This is amine. Same way, if I have Rx plus KCN plus minus, bond electrons transfer over here, product form is RCN plus KX. So here this is actually this X minus attached to Na plus, and so the product is NaX, here HX, here NaX, here HX, and here KX. This main product form is cyanide. Then if we talk about next nucleophile, which is KNO2, potassium nitrate, Rx plus KNO2. Again this cleave into two part, and the product form is RNO2 nitro plus KX. Same way, Rx plus AgNO2 silver nitride. Then again this cleave into two part, this is RNO2 and the product form is nitroalkane plus AgX. Same way, if I take Rx plus LiAlH4, this is known as reducing agent, means there is addition of H to this liberate H minus, this will liberate H minus. So this H minus acts as nucleophile over here, product form is RH plus X minus. And the last one, Rx plus RMGX, this is very important one. This is known as Grignard reagent, from the name of the scientist who discovered this. See, this is compound where you have alkyl chain also. metal also and halogen also. Now whenever there is cleavage, this cleave like this. Metal being electropositive always has tendency to liberate electrons. So metal always remains plus. So metallic part remains plus, Mgx plus. And this alkyl chain becomes negative. So here this alkyl chain acts as a nucleophile. From here bond cleave. So halogen electrons transfer on halogen, bond electrons. So now this will attack over here and the compound form is RR dash, alkane plus Mgx2 plus Mgx2. So this is the product form over here, alkane. Here also you are getting alkane. So these are the different types of nucleophile which can attack alkyl chain in the form of different. One more is there, Rx, when react with AgCN. See here KCN you are getting cyanide group. KCN you are getting cyanide group. But when we have AgCN, in that case this attach like RNC. Cn and C. As we discuss over here that Cn minus is ambident ligand, both the ends are enough capable for donating electrons and forming bond. So here in this case nitrogen is donating electrons, while here in this first case carbon is donating electron. When we have RCN linkage, that is known as cyanide, but when we have RNC type of linkage, this is known as isocyanide. This is known as isocyanide. So these are the two different things. Here in case of AgNO2 we are getting nitroalkane. That's it. So these are the different types of nucleophile when they attack on a haloalkane chain. Then the type of products which we are getting, that is cyanide, nitro, then alkane, isocyanide, alcohol, ether, amine. So these different products we will get. Now in detail we'll study about unimolecular and bimolecular nucleophilic substitution reactions. First we'll start with bimolecular nucleophilic substitution reaction and then we'll start with unimolecular. So first let me start with bimolecular nucleophilic substitution reaction. Now bimolecular means two molecules. Here in this reaction proceeds only in one step. Reaction proceeds in one step. Now both the reactants they are involved in this. So we have two reactants, Rx and Nu. Suppose for example I have CH3Cl as Rx. So this is my carbon. Here I have one hydrogen, then another hydrogen, and this is the third hydrogen, CH3, and here I have chlorine attached. Now nucleophile OH minus is attacking over here. Now this reaction proceeds only in one step. Here there is formation of one intermediate. To that will show as a transition state. Actually we can't say this as intermediate. This is an imaginary thing which is formed. So this OH minus attack on the carbon atom. See again this is halogen partially negative. This is carbon which is partially positive. Now OH minus is coming and attacking on the electron deficient carbon. So when this attack, here this carbon is a CH3Cl, all the 4 single covalent bond. What is hybridization of carbon in CH3Cl? Reply fast. What is hybridization of carbon in CH3Cl? sp3. Yes, correct, Ash. Hybridization of the carbon is sp3. What is shape of the molecule? Shape of the molecule. Yes, correct. Tetrahedral. This is the reason I have shown this molecule this way. Tetrahedral. See, this is the tetrahedral shape of the molecule. Right? Now, when OH minus is coming and contacting, this carbon convert into pentavalent state. On this side, I have chlorine present. From the opposite side, OH attack on the carbon atom. From the opposite side to that where my chlorine is attached, hydroxyl group attack on the carbon atom. And hydrogen, they arrange themselves in this kind of pattern. Right. So here my carbon is present in tetravalent state. From that this is converting into pentavalent state, and this pentavalent state of carbon is known as transition state. This is known as transition state. This is not an intermediate state because this is very unstable and you cannot isolate this one. You cannot isolate this transition state. This is an imaginary state. So this is not an intermediate. This is transition state. This is very unstable and you cannot isolate this. So once this is formed, as this is very unstable because in this transition state your carbon is pentavalent state and that is forming 5 bonds instead of 4 bonds. So this immediately undergo cleavage. Now here in this, actually this carbon and chlorine bond I'm showing by dash. Even carbon and hydroxyl bond I'm showing by dash. Carbon and chlorine bonds, that is partially break, and this carbon and hydroxyl bond are partially formed. They are in this stage, in transition state. CCl bond is partially break and COH bond is partially formed. Afterwards, bond between C and Cl break completely and C and OH form completely. After this, bond between carbon and hydroxyl form completely and carbon and chlorine break completely. And the product form is CH3OH. From CH3Cl, here we are getting CH3OH. This is chloromethane, which is getting converted into methanol at the end of the reaction. Along with this, Cl minus liberate over here as nucleophile. So this is the bimolecular nucleophilic substitution reaction. Because this is one step reaction, This is imaginary state. In this one step reaction, you see both the reactions are involved in the reaction, and so this is known as bimolecular. As both the reactant molecules are involved in the step, that this is known as bimolecular nucleophilic substitution reactions. Now here this haloalkane, this may be either primary haloalkane, secondary haloalkane or tertiary haloalkane, which will react fast. So if we see order of reactivity in this case, then primary halogens, they are highly reactive, then secondary, and then tertiary. Let me see why. See here what is going on. So OH minus is coming and contacting to the carbon atom from opposite side. OH minus, this is coming and contacting carbon from the opposite side, right? Now here in case of methyl, if we see this is a methyl chloride. If we have methyl, carbon is only attached to 3 hydrogen atoms. So there is very less crowd. If you have to go out nowadays, then it's very easy to drive vehicle because there is no much traffic is there. Same way when I have hydrogen is not taking much space, allowing OH minus to easily come and contact carbon which is surrounded by 1 chlorine and 3 hydrogen atoms. But instead if I have primary, in this case instead of 1 hydrogen I have presence of 1 alkyl group and 2 hydrogen atom and 1 chlorine. Now here this alkyl group is giving some crowd, right? Because of this OH minus is not that much easily attacked to the carbon as that attack in this case. Same way instead if I have secondary, presence of 2 alkyl groups are there. Instead if I have tertiary, 3 alkyl groups, which is creating more crowd. As more is the crowding, less will be the chances that OH minus comes or any nucleophile come easily and attack on the central carbon atom. And because of this, tertiary alkyl halides, they are least reactive, then secondary, then primary, then methyl alkyl halides, they react very easily to the carbonate, haloalkane. By which one? Bimolecular nucleophilic substitution reaction. One more thing is there, if you observe this reaction carefully, do you find any difference between reactant and product? If yes, write in comment box. Yes. Have you observed anything? No. See, the direction in which chlorine is attached, that is exactly opposite to that of hydroxyl group. Here in this case, chlorine is attached to right hand side, while here in product, hydroxyl group is attached on left hand side. So yes, this answer is correct. It's get inverted. The position of this nucleophile get opposite, and so because of this, suppose if the reactant is dextrorotatory, then the product becomes levorotatory. If your reactant is dextrorotatory, product becomes levorotatory. And so we can say that this reaction proceeds via inversion of configuration. This reaction proceeds via inversion of configuration, right? So if your reactant is dextrorotatory, your product is levorotatory. Second thing is rate of reaction. Actually, rate of reaction is directly proportional to concentration of reactants. Here, if you see in this reaction, you have two different reactants. So here my rate of reaction is proportional to, how we show concentration, in square bracket. So concentration of Rx into concentration of OH minus, both the raised to power 1. See here, two molecules are involved in this process. So this reaction is known as bimolecular nucleophilic substitution reaction. If I have to generalize this, then Rx is rate is proportional to Rx raised to 1 into Nu concentration raised to 1. So because of this reaction is known as bimolecular nucleophilic concentration reaction. Now we have to study about unimolecular nucleophilic substitution reaction. So about unimolecular nucleophilic substitution reaction, let me start. So in unimolecular nucleophilic substitution reaction, reactants as well as product, everything remains the same. Only the way how reaction carry out becomes different. Again, let me, for example, here we'll take CH3 thrice Br, that is tert butyl bromide, or else if I have to write IUPAC name, this is 2-bromo 2-methyl propane. How? See, I have one carbon which is attached to 3-methyl group, and to that carbon this bromine is attached. So this is 1, 2, 3, 2-bromo 2-methyl propane. OH minus is my nucleophile over here. This bond electrons transfer on bromine because that is more electronegative. OH minus attack on the carbon. So the product form is COH, CH3, CH3, CH3 plus Br minus. This even I can write CH3 thrice COH. So this is tert butyl alcohol or 2-methyl propane 2 all. Now this unimolecular nucleophilic substitution reaction, this proceeds via 2 steps. Here in this case, intermediate form during reaction. So this reaction takes place in 2 steps. Step 1. In First step, under the effect of protic solvent, your this tertiary butyl bromide undergo bond cleavage. So this bond electrons transfer on bromine. This is first step. This is reversible step. Here your carbon is tetravalent, forming 4 bonds, sp3 hybridized. When this is losing one Br minus because of heterolytic cleavage of bond, formation of CCH3 thrice plus. What is this? Name this species. Write the name of this species in comment box fast. Write name of the species CCH3 plus in comment box. Right name of the species. I didn't get any answer till now. Name of the species form. Don't know CCH3 thrice plus. That is known as what? That is carbocation. That is carbocation. No Sanvi. This is carbocation. Carbon bearing positive charge. That species is known as carbocation. So here during step 1 in unimolecular nucleophilic substitution reaction, there is formation of carbocation. Now again, you people know very well, here your carbon is in trivalent state. You even know the structure, that is distorted triangular planar because of availability of one p orbital which is vacant, and due to that only you have one positive charge over here. This is unstable. So as soon as this form in the reaction mixture, this go for step 2. In step 2, this positively charged carbocation get attacked by negatively charged nucleophile. This is electron deficient. Here OH minus, which is nucleophile, that is electron rich. So immediately this attack on electron deficient carbocation carbon and form. Now here if you see, 2 different possibilities are there. If I have to draw structure of carbocation, then this is the carbon 1, 2 and 3. This is attached to another carbon. But this p orbital is vacant and this is carrying positive charge. This is the structure of carbocation. This p orbital is completely vacant, while these are filled orbitals which is utilized in bond formation. As this is not taking part in the hybridization of carbocation, if you see, that is sp2 hybridized. Now this is vacant orbital. Here OH minus is coming and contacting. Now there is equal possibility that OH minus attack on either left side or that may even attack on right side. So if this will happen, this is the CH3OH, then or these two different possibilities are there, and both the possibilities, they have equal chances. So during this reaction, 50% of this and 50% of this will form. Both the products, they form in 50-50% ratio. So if this is dextrorotatory, then the another one is levorotatory. So in your reaction mixture, you will get 50% of dextroisomer and 50% of levoisomer, and this mixture is known as, write your answer in comment box, mixture where you have 50% dextro compound and 50% levo compound is known as, write in comment box. Yes, Priyal, racemic mixture. So at the end of the reaction, you will get racemic mixture. What is the speciality of racemic mixture? Write fast. What is the speciality of racemic mixture regarding its optical property? Regarding its optical property, what is the speciality of racemic mixture? Write fast. Yes, correct, Hitanshi. Racemic mixture is always optically inactive because of both the isomers, they are present in 50-50%. So if this rotate plane of polarized light towards right hand side by some angle, by the same angle this will rotate in the left side, and so total rotation is 0. Total rotation is 0, and because of this mixture is always optically inactive. One more thing, here in the first case when we study biomolecular nucleophilic substitution reaction, we discussed that this reaction proceeds via inversion of configuration, while here in this reaction we'll get racemic mixture at the end of the reaction. This proceeds in one step, bimolecular, while unimolecular reaction, this proceeds in two different steps. Now if we talk about rate of the reaction, here rate of reaction depends on concentration of reactant. Same way here also, rate of reaction depends upon concentration of reactant. But in first case only one step reaction was there, so there was no any confusion that which we have to consider for taking rate of reaction. But here in this case, if you see, you have two steps involved in the reaction. Now whenever we have reaction which is carrying out in more than one step, in that case we have to take slow step in consideration. The slow step in the reaction we have to take in consideration for taking out rate of reaction. Now we know that once carbocation is formed, as that is unstable, this readily get attacked by nucleophile and form product. So that is fast step. Second step is fast step, but formation of carbocation is a slow step. Formation of carbocation is a slow step, and always a slow step is rate determining step. Always slow step is rate determining step. So this is step 1 is rate determining step. If you see in first step, the reactant involved is only 1, and so here rate is proportional to only concentration of Rx raised to 1. While in case of bimolecular reaction, that is proportional to concentration of both the reactants. So that is bimolecular. Here this is only dependent on concentration of one reactant, and so this is known as unimolecular nucleophilic substitution reaction. One more thing we have to discuss in unimolecular nucleophilic substitution, as we discuss in case of bimolecular nucleophilic substitution reaction, that reaction, primary alkyl methyl alkyl halides, they give reaction at the highest rate. Then tertiary alkyl halides, the rate of reaction via bimolecular nucleophilic substitution reaction is very low, while primary and methyl, they have very high. Here let me see. Now as you see, this reaction proceeds by formation of carbocation, and we have one rule that more is the stability of product, higher is the rate of formation. More is the stability of product, higher is the rate of reaction, and here rate of reaction is completely dependent on first step, and in first step your product is carbocation. So whichever carbocation is more stable, that will forms at highest rate. Now as per your knowledge, which carbocation has higher stability, primary, secondary, tertiary or methyl? Which carbocation has highest stability? Write your answer in comment box. Yes, correct Ash. Tertiary carbocation has highest stability, and as per that, here in this case, tertiary alkyl halides, their reactivity is highest. Tertiary alkyl halides, their reactivity is highest. So in this case, tertiary, then secondary, then primary, and then methyl. This is about unimolecular because of stability of carbocation form. While in case of bimolecular, this is in the opposite way. Tertiary, secondary, primary, and highest in case of methyl, right? So CH3 thrice X has highest reactivity, then CH3 twice CHX, then CH3 CH2X, and then CH3X. Opposite to that, CH3 thrice CX has lowest, then CH3 twice CHX, then CH3 CH2X, then CH3X. Get it? So this is about order of reactivity of unimolecular and bimolecular substitution reaction, that depends upon type of alkyl halide present. Based on that, we can decide that this will follow which mechanism. If I have tertiary alkyl halide, this proceeds via unimolecular nucleophilic substitution reaction, and if I have primary alkyl halide, this proceeds via bimolecular nucleophilic substitution reaction. Hope this is very clear to you all. Now for this bimolecular and unimolecular, instead of writing this much lengthy name, we use short terms SN1. Here we have to read like this: unimolecular nucleophilic substitution reaction. Unimolecular nucleophilic substitution reaction. And for bimolecular, we use symbol SN2. Bimolecular nucleophilic substitution reaction. So to these two reactions, in short, we say SN1, SN2. So this is my SN1, this is my SN2. Now we even have allylic and benzylic haloalkane, haloarene. This show even high reactivity. This show even high reactivity towards SN1. Why? Because these carbocations formed from these molecules, they are stabilized by resonance due to stabilized through resonance. If I have allylic halide, that is what? CH2 double bond CH, CH2X. When these get cleaved, the carbocation form is CH2 double bond CH, CH2 positive. When this, so this is minus X. This is the carbocation form. Now this carbocation is stabilized. How? So here in this case, this pi bond, they shift from carbon 1 and 2 to 2 and 3. So because of this, I have one more resonance structure, that is CH2. Now this becomes plus this double bond transfer between second and third carbon. This way, this is stabilized by resonance structure. Higher is the number of resonance structure, higher is the stability of the molecule. And as per this law, these are more stable even than tertiary alkyl halide and has higher reactivity towards SN1. Same way benzylic, if we see, benzylic alkyl halide is CH2X. When this get converted into carbocation by removal of these electrons, this is CH2 plus. Now this will donate electrons over here. Because of this, then so this is how this carry these many resonance structures which result in extra stability, and because of this, stability of the carbocation increases and is more reactive towards nucleophilic substitution reaction by SN1 method. Even if we have to see the activity of alkyl halide, so if I have different halogens present, then alkyl iodides are higher reactive than alkyl bromide, then alkyl chloride, and least is RF because of bond enthalpy is more in this case. So this is what is about unimolecular and bimolecular nucleophilic substitution reaction. These reactions are very important from your board exam point of view. So refer these reactions, solve number of questions based on this. This time in board exam they ask a 5-mark question where they had given one para from this reaction, from these reactions, and then based on that para they ask number of questions and you have to answer those questions, and that whole para is from these 2 reactions. Here I'm ending my today's session. Homework I'll WhatsApp you, go through that. That's